So continuing on with lesson 1 of module 14, we have page 3. So we're starting with example 2, and we're just going to look at writing each of these decimals as a fraction or mixed number. So here we have for A, 0.355. And if we state that decimal correctly, like I really encourage you to do every time you see these decimals, we would actually say this decimal as 355 thousandths, because that last 5 is in the thousandths place. So for this particular decimal, because we say that decimal as 355 thousandths, that is our fraction. So 355 and 1,000 is our denominator, because that's the place value of this 5 right here. So I know that that is the correct fraction for that decimal, but what I want to do now is simplify it down as far as I can go. So I'm going to do that. Well, I know that both digits are divisible by 5, so I'm going to divide them both by 5. So 355 divided by 5, and this is where when you're working this out, you can use a calculator to do this, but for everything else, I ask that you do not use your calculator. So 355 divided by 5 is 71, and 1,000 divided by 5 is 200. And now I'm looking at that denominator of the numerator of 71, and I know that 71 is a prime number, so therefore I cannot simplify this any further. My simplified fraction is 71 over 2,000, or 200, excuse me. All right, and then for B, we have 0.43 repeating. So we have 43 hundredths that's repeating. So just like before when I showed you that algebraic way by writing an equation to turn this into a fraction, we can do that here. So again, I'm going to start, and I'm going to just use n because that's representing the number. So n for number, I'm going to let n equal 0.43 repeating. But what I want to do is multiply both sides by 100, because my whole goal here is to get 43 as my whole number. So I'm going to multiply both sides by 100. So I've got 100n now. 100 times n would be 100n, and then I'm going to multiply this times 100, which moves my decimal point to the right 2 places. So now it's 43.43 repeating. So I'm going to take away 1n, and I'm going to take away the value of 1n, or n, which is 0.3 repeating, from this side. So 100n minus 1n is 99n. And on this side, 43.43 repeating minus 0.43 repeating is just 43. So 99n equals 43. To get n by itself, I need to divide by 99. Divide by 99 on this side, therefore n is equal to 43 over 99. And now recall, at the bottom of, page 3, page 2 actually, I had shared how if you have 2 digits repeating, your denominator will be over 2 nines, or 99. And we can see here what we just found, that n is equal to 43/99. So now looking at C, 0.8 repeating. Well, in C, we only have 1 digit that is repeating, so that tells us that our denominator here is going to be just 1 9. So we know that our denominator here is 9, and our numerator is 8. Now I could have gone through the algebraic way of what we just did in B with C, but using what we know about those repeating digits, we can also just conclude here that 8/9 is the fraction equivalent to 0.8 repeating. I ask that you pause the video and try 4, 5, and 6 on your own, and then play the video and continue on and check your work with mine. So I see here number 4, when I say this decimal, 12 hundredths, or 0.12, saying it correctly, 12 hundredths, that is my fraction as it is stated. So 12 over 100. And what I need to do now is simplify it. Well, both 12 and 100 can be divided by 4. Therefore, my numerator is 3, and my denominator is 25. So 3/25 is 12 hundredths as a fraction. Number 5 here, we have 0.57 repeating. So again, we know that because it has 2 digits that are repeating, it is going to be over a denominator of 99 and 57/99. 57, although it is odd, it is not prime, and it is divisible by 3, because I know that if I take 19 by 3, I get 57. So I'm going to divide both numbers by 3. Therefore, my numerator is 19, and 99 divided by 3 is 33. So 19/33 is 0.57 repeating as a fraction in simplest terms. And then for number 6 here, we have 1.4, or 1 4/10. So I'm going to write that out in word form just so that I can see it. 1 4/10. Well, 1 is my whole number, and 4/10 looks just like this, 4 over 10, but I know that 4/10 can be simplified by dividing both the numerator and denominator by 2, so that actually just becomes 1 2/5. Or I could write it as an improper fraction, and it would be 7/5. Either of those is correct. Now, we're kind of slightly switching topics, and we're going to be talking about finding square roots and cubed roots. So before I begin, I would like you to maybe just take a minute and think about, have you ever heard the term square root or cubed root? Or do you know how to find one? Or do you know what it is? If you don't, that's okay. So let's start. So let's start with square roots. So to square a number, we're going to take a factor and multiply it by itself. A square root is a little different. It's the opposite of squaring. To find the factor that can be multiplied by itself to result in that number, we're going to use the symbol, this square root sign, which is technically called a radical. every number has two square roots. There's a positive root and a negative root. The principal square root is the positive square root of that number. And this is the one that is used most often. If the square root is already written for you, then the answer is always the principal square root. So let's think for a moment, what about the square root of a negative number? Give me a second, I gotta adjust the page for you. So let's use some examples here for a negative square root. So the square root of negative 16. Well, we know that the square root of 16 is 4, because 4 times 4 equals 16. But it's not equal to 4, because we know that 4 times 4, right, a positive times a positive equals positive 16, and a negative times a negative times a negative is also positive. Therefore, we cannot have a square root of a negative number. So you cannot have a radical with a negative number within that. We call these imaginary numbers. Now, a perfect square is a number that can be written as an integer to the second power. And it is a number that has integer square roots. So let's list out the first 15 perfect squares. Well, 1 times 1 is 1, or 1 squared is 1. So 1 is a perfect square. Going on, well, 2 times 2, or 2 squared, that's 4. 3 times 3, that's 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. And so on. 7 times 7, 64 is 8 times 8. 81. 10 times 10 is 100. 11 times 11 is 121. We've got 144. 13 times 13 is 169. Then our last two here, we've got 14 times 14 and 15 times 15. So these are the first 15 perfect squares. So knowing that 225 is 15 times 15, can you add to my list and generate more perfect squares? I'd like you to see if you can add to my list. So How can you generate more perfect squares, though, to really just put it in word form? You can just take any integer and multiply it by itself. And the result of that, because you're multiplying it by itself or you're squaring it, the result is what we call a perfect square. So I ask you to find the perfect square for 22. So what is 22 squared? I'm going to leave you with that as you finish this video.